Hi there, welcome to lecture 4 of Machine Learning from Data, where we're going to answer the question, is real learning feasible? Okay. Now to know what that means, we need to recap last lecture. So, in the last lecture, we analyzed the learning scenario where you have a fixed, unknown target function f and a fixed hypothesis h, fixed. In other words, you can't change it once you see the data. Okay. And then the question was, is this hypothesis good or bad? Can we certify or can we verify whether or not that hypothesis H is good or bad? And we showed that, the scenario is equivalent to a bin model / sampling scenario where the bin corresponds to the whole input space. Okay. And in this input space are points, and these points correspond to marbles. Some of these points are green if H is equal to F, so those are green marbles. And some of these points are red if H is not equal to F, so those are red marbles. And we're very interested in this red region. In particular, we would like to know, is it small? Does H approximately equal to F almost everywhere? Okay. And so we define the out-of-sample error as the probability that if you generated a point in the space, according to this probability distribution that generates data, if you generated a random point, what's the probability you'll get a red point? Okay, and that in some sense quantifies the size of this red region, which we would like to know. We can't because we don't know F. Okay, but we can sample a data set. So we sample a data set, and in this data set, we do know F, we do know the Y values which correspond to F on the data points. And some of the data points are red if for our H, they don't agree with Y, and some of the data points are green. So we can calculate the fraction of red data. Okay. And this we call the in-sample error. Okay, the fraction of errors made by our hypothesis H on the data. Okay, now, the question is, does this in-sample error tell us something about the out-of-sample error, the size of this red region? Okay, and that's where the gift from Hoeffding came to us. Okay, and Hoeffding said, yes, you can, providing you're willing to give up the for sure, so we'll never know for sure what Eout is, and providing you're willing to give me some error tolerance. Okay, so within some error, we can conclude that Eout is approximately equal to Ein. So Ein reaches from inside the data to outside the data and tells us something about Eout with high probability. And exactly how high a probability? Well, it depends on the sample size and what's the error tolerance. If you give me a larger error tolerance, for example, if the error tolerance is 1, then for sure. But as you make the error tolerance smaller and smaller, it's becoming harder and harder to make that conclusion, unless you have more and more data. Okay? And the precise dependence on n and epsilon squared is this exponential that came from Hoeffding. Okay? But that's not real learning, that's verification. You fix a hypothesis H, and if it has a low in-sample error, great. You've got a good hypothesis. If not, too bad. But you can't change that in-sample error now because it's fixed. In real learning, we get the data, and then we go through our hypotheses, and we see if, one of them will have a low in-sample error. So the setup is very similar, except that now we have many hypotheses, and we're going to consider today a finite number of hypotheses, and each hypothesis corresponds to exactly the kind of bin that we just saw. So each hypothesis is a bin with a red region and a green region, okay, and they can all have different sizes of red regions, so different Eouts. Okay. And then we sample the data. Okay. Now, once we sample the data tells us for each hypothesis, we can compute the fraction of red data points, so we can compute its in-sample error. And then we scan the hypotheses, and in this example, you see that the second hypothesis, H2, got an in-sample error of 0. So now we pick that hypothesis as our final hypothesis, G. Okay. And then the question becomes, is G good? In the learning sense. In other words, does G approximate F? Is Eout of G small, i.e. is Eout of G approximately equal to Eout of H? So because why did we pick H2? Because it had 0 in sample error. Okay, and the complication here is that we exercise this choice, we exercise this ability to pick a hypothesis based on the data, and that violates Hoeffding. So we cannot apply Hoeffding. So we'll need some other analysis. It turns out that it's not a hard adaptation of Hoeffding, okay? But we cannot apply Hoeffding. And as a sort of intuition for what goes on, try this problem. Okay? So you've got 1,000 monkeys behind closed doors. Okay? But you have 1,001 doors because behind one of the doors is a child. Now you administer an A/B test, okay, with 5 questions. Monkeys answer randomly. The child gets it all right because the child is smart. Okay? But now all you can do is observe the number of questions that each door got wrong. Okay, so, in this example, the first door got 2 wrong, the second door got 3 wrong, and then the third door got 0 wrong. Maybe that's the child. But you keep going. Okay, then there's 4 wrong, then 0 wrong again. Maybe that's the child. Okay, and you keep going, and you keep going. So, the question you should ask yourself is, what are your chances, based on the number of questions that were gotten wrong by each door, what are your chances of getting the child? What are your chances of picking the child? That corresponds in the learning scenario. We're going to look at the in-sample error, and we're going to pick whatever looks best according to the in-sample error. What are our chances that we did get the true, genius hypothesis that approximates F? Okay, what are your chances to get the child in this question? Now you can compute this probability. You can compute your chances of picking the child, assuming that among all the 0 wrong doors you pick randomly. But the important thing here is to realize that there'll be many doors with 0. Only one door contains the child. So how come there are many doors with 0? It's because many of these monkeys just happen to get it right by luck, by sheer dumb luck. Okay? And so for those monkeys, E in is not equal to E out. But you're just as likely to pick one of those dumb lucky monkeys as you are the child. And if you pick the dumb lucky monkey, its E in is 0 and its E out is 0.5, random. But if you happen to pick the child, then its E in is 0 and its E out is 0. So E in is equal to E out for the child, but not for the monkeys yet. There'll be many, 0 doors. You'll probably pick a monkey. Okay? And so clearly, it's not the case that in this scenario, with high probability, you will find that E in is equal to E out, like Hoeffding gave us for the verification scenario. Okay, so something needs to be done if we're going to conclude that E in equals E out or approximately equals E out for the learning scenario like this. And you might ask, okay, so what can we do about it? Okay, what can we do about it? In this particular case, you might ask yourself, what can we do about it? We want to pick the child. Okay, what can we do about it? Okay, but I'll tell you a fact. The more monkeys there are, okay, the more monkeys we have, if we had not 1,000 monkeys, but 10,000, 1 million, an infinite number of monkeys, the more monkeys there are, okay, the more likely it is that a monkey that there'll be many monkeys which get 0 wrong. Okay? And it's even less likely now that E in will reach to E out. Okay? So this notion of, when you have many choices to pick from, the fact that some of them may get lucky out of sheer dumb luck, creates a huge barrier to being able to reach from the in-sample error to the out-of-sample error. That's what we're going to address today. We're going to go to the board. It's an important lecture. The board will slow me down. So pay attention. It's a good idea to grasp what's going on in this lecture, because at the end, we're going to sort of interpret the result we get, and then we're going to reduce it to a very simple process, a 2-step process for learning. Okay, so today's main goal is to see if we can prove a sort of a Hoeffding-like inequality for the real learning process. So goal. For real learning, can we conclude that E in of G, now remember what G is. G is the guy that results from the learning. So you have your hypothesis set and you use the data to pick G. Can we conclude that E in of G is approximately equal to E out of G, with high probability? So we've already given up the for sure. So from now on, when we talk about, whether or not we're going to do learning, we always are in this world of with high probability. So with high probability. Okay, now what's going to be the end result? Okay, so we're going to prove a similar result that we proved for Hoeffding. So we're going to prove. So what's going to happen? You do learning, you produce G. You look at E in of G, and then you're going to say, this E in of G is small, so this is a good hypothesis. This G is good, so G is approximately equal to F, i.e. E out of G is small. So that's the good thing that could happen. A bad thing could happen is when you claim that, E out corresponds to my E in, you're completely wrong. Okay, so we want to prove, and this is what we will end up proving. And I will highlight the differences between what we're going to prove and what Hoeffding gave us for a fixed hypothesis H in the context of verification. So we are going to prove, that the probability, of a bad thing happening, so that's the same as before, the probability of a bad thing happening, is small. Okay, so that's the same idea, that we had before. And when we say is small, what we mean is less than equal to something. Something. Okay, and what was that something in the case of Hoeffding? In the case of Hoeffding, it was twice e to the minus 2 epsilon squared n. Okay? And, the epsilon came in defining what was a bad thing. Okay, and the n was the size of your data set. Okay, so when we're done, what we're going to prove is that the probability of a bad thing, so let's first define a bad thing. So you've produced the final hypothesis. So it's, and then you're going to claim that by looking at E in of this final hypothesis G, that's the E out. Okay, so a bad thing occurs if E out of G, okay, minus E in of G, okay, is in magnitude. So if there's a big deviation between E out and E in for G, so if that's big, okay, if that's greater than epsilon, that's a bad thing. Now, why are the G's in red? Okay, so the G's are in red because previously the Hoeffding had H in here, the fixed H, fixed as in it does not change after you see the data. G, on the other hand, is not fixed. It changes after you see the data. In fact, it's picked according to the data from the hypothesis set. Okay. So what we want to say, okay, is that the probability of something bad happening should be small. Okay. And for the moment, we're going to focus on exactly what we showed in the slide that we just showed, which is that let us imagine that the hypothesis set is finite. Okay. Then we're going to show that something almost equivalent to the Hoeffding bound is true, except that we have to increase the size of this small. So now a bad thing is more likely to happen. And that makes sense because we have, think of the monkeys, think of the coins, right? It's possible to get unlucky and, by accident find a monkey who got all the 5 problems correct. Okay? And that monkey is no genius. Okay. So we need to account for this notion of choice, and what plays the role of choice is the size of the hypothesis set. So we inflate this small number by the size of the hypothesis. And once we put the size of the hypothesis set, it's a very similar looking, guarantee to the Hoeffding guarantee for the fixed hypothesis set. But now it applies to learning. It applies to the G. So G is new, and the size of the hypothesis set comes into account for the fact that G is chosen using the data from the hypothesis set. Okay. And this here is, at the end of the day, the entire reason why we needed to fix the hypothesis set H, because otherwise we can't put a size in here. Okay, and then we won't be able to conclude, we won't be able to reach from E in, which is an inside the data quantity, which we can measure, to E out, which is what we would really like to know in order to decide whether or not, G is approximately equal to F. So this is what we will prove. Similarly, there's the equivalent thing, which says that the probability of a good thing happening, which is the probability that E out, minus E in, is less equal to epsilon. Okay, and that's going to be at least 1 minus twice e to the minus 2 epsilon squared n. Okay, where in order to get things correct, I need to put, I would like to make this claim for G. So I would like to make this claim for G. Okay, and I need to plug in the size of the hypothesis set. So the bound looks very similar. Okay, it's applying now to the result of learning G, but it got worse by a factor H. Okay, so that's what we want to prove today, and that'll establish that at least with a finite hypothesis set, learning is feasible. Real learning is feasible. Once we do that, we'll then massage this bound and interpret it in various ways. And then lastly, we're gonna, bring the learning setup a little bit closer to reality by considering, different ways in which we can measure error, not just the probability of getting it wrong. And we will consider the fact that, there might be noise in the data, so the target function may not be a deterministic target function. And we'll end with a similar flowchart for the learning problem setup that we had before, but now we will introduce the new ingredients that allow us to conclude that learning is feasible. Real learning is feasible. So, for now, let's prove this. And we're going to box this, because this is golden. This establishes that at least we can reach from inside the data to outside the data to at least verify that the final hypothesis from real learning is good. And we can verify it by looking at E in, because E in is close to E out. Okay, now the proof is going to use some tools from probability theory. Okay, and they're basic tools, but I'll just summarize them in case you haven't seen them. I don't want anyone to get lost just because they haven't seen these tools. Okay, so let A and B, A and B be events. Okay, so now in the formal theory of probability, events correspond to sets. Okay, and we say that the event A implies B. For example, it's raining implies I have an umbrella. So there's the event it's raining, there's the event I have an umbrella. So you can think of an event A implying B. This is the subset relation. This means that, A is a subset of B. Okay, because, if you know that an outcome is an event A, it must be an event B. So that means that A is a subset of B. Okay. And this means that the probability of A is at most the probability of B. This is always true for the subset relationship. The probability of a subset cannot be larger than the probability of the superset event. Okay? And that is related to the logical notion of implication. Now, here's another important notion, the notion of union. So if you have events A and B and you take the probability of the union, so that corresponds logically to the OR. So A or B, that corresponds to A union B. Okay? And the probability of a union B, is at most the sum. Probability of A plus the probability of B. Okay, and we will call that the union bound. Okay. And lastly, and I'll just list it here, although we won't need it today, that there's what's called Bayes' theorem. So it relates to conditional probabilities, which is useful in inference, which is useful in machine learning. So the probability of A given B is equal to the probability of B given A divided by the probability of B. Probability of B given A times the probability of A divided by the probability of B. So this relates, a conditional to the transposed conditional. It allows you to compute one conditional in terms of the other conditional if you know the prior probability. Okay, so some fundamental facts from probability theory. Now let's go ahead and prove this. Okay. So remember what happens. You have a hypothesis set, H, you get the data, D, and you produce G. Okay. Now, if this G didn't depend on the data set, okay, then, we can apply Hoeffding. So let's for the moment look at the hypothesis. Let's look at hypothesis H1. So certainly, if we fix the hypothesis to H1, then we can conclude that, the probability that Eout of H1 minus E in of H1, this probability, the probability that this thing is that a bad thing happens for H1, so the probability that a bad thing happens for H1, okay, because H1 is fixed, it doesn't change when you get the data set. So the probability of a bad thing for H1, well, that's at most 2 e to the minus 2 epsilon squared n, and this is just Hoeffding. Okay, so, and, there's nothing special about H1. So the hypothesis set has H1, H2, H3, up to H sub m. So we're assuming the hypothesis set is finite. Okay, so it has a finite size m. So this same inequality holds no matter which specific fixed H I decide to choose. So the probability of, Eout of H sub I for a, any fixed member of my hypothesis set minus E in of H sub I is greater than epsilon. Well, that's going to be less equal to 2 e to the minus 2 epsilon squared n. And this is again Hoeffding. Okay. And the reason is that, any specific hypothesis in my hypothesis set does not depend on the data set. The problem is that G depends on the data set. Okay. So we define the bad event. Okay. So the bad event. Okay. How did we define the bad event? The bad event is the outcome that for G, E out of G minus E in of G is greater than epsilon. Okay. So E out of G minus E in of G is greater than epsilon. So this is the bad event. Okay. That's the bad thing. We'd like to get a handle on the probability of this bad thing happening. Okay, but now look, we made this fundamental assumption, okay, that G has to come from H. Okay. So let's look at this. If you're in the situation of a bad event. So if, let's call this bad event, B. So B sub G. So this is the bad event B sub G. Okay. If B sub G occurs, so if the bad event occurs, well, we know for sure, and this is why we impose the restriction that G must come from the fixed hypothesis set H. We know for sure that G is one of these H's. Okay. So if the bad event occurs, then the bad event occurs for one of the H's. Then the bad event occurs for one of the H's that are in big H. Okay. So what does that mean? That means that this bad event, E out of G minus E in of G greater than epsilon. So that bad event implies, okay, that E out of H1 minus E in of H1 is greater than epsilon. Or E out of H2 minus E in of H2 is greater than epsilon. Or E out of HM minus E in of HM greater than epsilon. Okay. And why is that? For the simple reason that this guy is one of those. So if this guy is bad, in other words, its out of sample error deviates a lot from its in sample error, then it means that one of those must be bad. So this or must be true. So this implies that. But we just stated the implication bound. So this is called the implication bound. This is called, by the way, the union bound. Okay. So, what can we conclude? What we can conclude, okay, so conclusion. So, the conclusion. Okay. And now I'm going to use the union bound. So, since this event implies this massive OR, it must be that the probability of this event is at most the probability of this massive OR. So, the conclusion is that the probability that your bad event occurs the probability that there's a deviation between E out and E in for G is at most, okay, the probability of this union, but the probability of this union or the probability of this OR is at most the sum of those probabilities. So it's at most the probability that E out of H1 minus E in of H1 greater than epsilon plus the probability that E out of H2 minus E in of H2 greater than epsilon plus the probability that E out of HM minus E in of HM greater than epsilon. Okay? So this probability of a bad event is at most the probability of this OR. Okay? And the probability of this OR is at most the sum of the probabilities of the individual events in the OR. But this is less equal to, and we just argued it because this guy is fixed. It obeys the simple Hoeffding bound. So this is less equal to twice e to the minus 2 epsilon squared n plus twice e to the minus 2 epsilon squared n plus plus twice e to the minus 2 epsilon squared n. And how many of these are there? There are m of them. So this is equal to 2m e to the minus 2 epsilon squared n. Ta-da! Okay. Miracle! Okay. Now, some of the things that made this work are the fact that the Hoeffding bound applies to each individual H, okay, and the bound for each individual H, in some sense, does not depend on H. Does not depend on properties of H, like its actual out-of-sample error, or even the specific in-sample error. We just say that, if the deviation is epsilon or greater, if the deviation is greater than epsilon, that cannot happen very often. And it's the same small probability for all the h's. Okay, some of the power of the Hoeffding bound. Okay, and then you just add these up, you get twice m. But whoa, this m is just exactly the size of the hypothesis set. And there, it's not a hard proof, but it's conceptually a very important proof. It shows that if we increase the probability, we can get a bound on the probability of a bad event for G. Okay, the result of learning. So the output of the learning, which is the final hypothesis G, which is picked from H, the in-sample error for that final hypothesis is approximately equal to the out-of-sample error for that hypothesis, with high probability, where the high probability is now not as high as it was before. Okay? Because now we're subtracting a larger thing from the one. Or the probability of a bad event is small, but not as small as it was before when you fixed a single hypothesis. So we have explicitly quantified the price that we have to pay for picking a hypothesis from the hypothesis set using the data. And as a general principle, whenever you exert any amount of choice, and in this case we're exerting a choice among all the possible hypotheses that are in the hypothesis set, whenever you exert any amount of choice and the data is what influences the ultimate choice you make, you have to pay a price. And we've quantified that price you pay when you pick a final hypothesis from the hypothesis set. Okay? So let's keep this important formula here. Let's erase everything else and let's come back and interpret the heck out of that and see what it means for learning. Okay, so speed erase. The first thing we're going to do is massage this formula into a sort of more useful form, one that you may be familiar with, okay, and then we'll interpret it.